My talk is about knowledge graphs, and it's called Knowledge Graphs for the Greater Good, because we're going to have a look a bit into what knowledge graphs are, how to construct them, what they are, how they're built, and also more specifically, and that's really important to me, how to use them to do good things in the world, right? So the subtitle is How to Save the World from Ignorance. So we're going to talk a bit about what actually can be done to make the world a better place with knowledge graphs. So talking about knowledge graphs, just imagine you're going to the movies with a few friends of yours, and what you want to achieve is to seat them in positions in a one-dimensional space so that you know, everyone is pretty happy with their neighbors. So you could just start by constructing a small graph with all your friends. Some of them might be good friends, some of them might be in a relationship, some of them even might have a one-way crush to each other or to one of the other people, and some might be just acquaintances. So what you actually want to do is, let's say you want people who are in a relationship to sit next to each other. Obviously, you probably want to avoid people who have a one-way crush to sit next to each other, because that could make an awkward situation. Acquaintances probably just space fillers, or it's not too important how they sit. So you could construct a knowledge graph and look into what is the optimal positioning for those, right? So then when you end up going to the movie, if you're anything like me and you end up in a situation where in the end everyone just sits randomly, you might be very annoyed with that. But you can see on this very simple example how knowledge graph can actually help you in very simple setting as well. So before we really delve into knowledge graphs as a topic, it's, I think, very important to look at the broader research field as well, which is called the Semantic Web. And the Semantic Web has been around for now about 20 years. So it was the turn of the millennium when Tim Berners-Lee actually came up with a vision for the Semantic Web that involved kind of a new generation of web that is not only readable by humans, but can also be understood by machines, right? Up to that point, we had mostly artificial intelligence that gave us a way to handle data. But the semantic web was a totally different approach, as you will see, right? So thinking about today's web and how it looks like and how it is designed, it is all just about the user, right? The web today assumes that only a human being is actually browsing it and looking at it from a user perspective. So it's generated just to present information from a database that can be read by a human being, and there is not a lot of structural information in it, really. So if you just think about typical use cases on the web, right? So as we know, most people spend more than 90% of the time of the web browsing social media, like Facebook, Instagram, and Twitter. And we'll come back to that because this involves bigger problems as well for humanity. But when we think about searching information, you know, you normally browsing blogs and news and just normal web searches to get to the information you need. You also use online shopping probably quite a bit, and all those interfaces are designed for human beings. So if you want to compare prices, for example, right, you will have to go to different websites and do it on your own. Or, you know, if you're consuming news from social media, for example, it's your own responsibility basically to verify truthfulness of this type of information. So these are all things that might be problematic. And also all those things might be made better or more efficient by the semantic web. So the problem here, as what I was trying to line out, is we have no semantics, right? Nothing is really machine understandable because you have to follow all those links yourself and get to the information you actually need all by yourself. And also that makes it pretty hard for data providers to share data, right? Because just imagine someone's publishing data on the web. They might just have a PDF and just, you know, publish it on a website, on a link, and there might be some very, very valuable hidden information inside of that, but there's no way for a machine to really access this information that's hidden on a link on a website in a PDF. So it's really, really hard work also for humans to browse all this data and to find these hidden gems on the web that they're actually looking for, right? So just imagine you might have a health issue and looking on the website of your healthcare system in your country, and it can be really tedious to find a very specific information that actually affects you on the web when you have to follow all those hundreds of links maybe until you actually get there where you want to be. So the vision of the semantic web is that you attach meaning to all this data that you have published on the web. So thinking back in previous talks, you might have heard about Google's Knowledge Graph, which actually made this term knowledge graph really popular about a decade ago. And also Wolfram's Alpha search engine, maybe not that popular, but this is actually the company that brought us Mathematica as well. And they have really advanced semantic search engines running as well. So, so the goal here for the semantic web is to provide information that can be processed by computers, right? And if you're just guessing now, you might be right by guessing that somehow this will be a knowledge graph. So we have kind of a graph structure that can be followed easily by a machine, and following all those nodes, you might end up at the information you need, which is also possible for a computer to do. Right, so computers can integrate this kind of information from the web and give you the piece of information that you're actually looking for. Yeah, just let's have a look at an example, right? Let's say you're trying to do a conversational chat with a knowledge graph system. Let's say if you have a look at this picture here on the left side, it's your messages, on the right side, the messages from the agent. So let's say you want to travel to New York for 2 days before Thanksgiving and stay for a week. So that's what you type in a text chat to the chat bot that is querying the knowledge graph, right? So from a normal perspective of the web right now, it's pretty hard for a system to recognize Thanksgiving as a date, or New York as a destination. But following the knowledge graph, if you have a look on the right side of the picture, the bot could derive that New York has an airport called JFK Airport. It can see that Thanksgiving is actually on the 22nd of November. And it can basically come back to you and say, okay, there are flights to New York at this date. Where will you be flying from? Right, then you come back and say, okay, I'm from San Francisco. And I also want, by the way, a non-stop flight, and I want to fly first class. So the bot would extract this information, San Francisco, non-stop and first class, put it in the knowledge graph as a query again, and come back with some concrete flights, like for example the Delta 2648 flights that fits the filter that you set for non-stop and first class. So it comes back to you and says, oh, I got it. I found some flights for you. List the flights. Then you browse them and decide if you like them or not. And then you notice, for example, actually I don't want to leave in the morning. I would prefer to leave in the afternoon. Not that much of an early riser. So so you say, okay, I would prefer to leave in the afternoon. And again, the system goes back, adapts the filters, and comes back very quickly with a result. Right, so this is a very intelligent form of querying data that doesn't really require you to take care of all those little things like, comparing flights from different airlines, trying to find all the criteria that you want to know, even deciding which exact airport in a city you want to fly to. So, I mean, personally, I've been using this a lot. And can be really time consuming to find the exact flights that you want by comparing all the prices and destinations and so on. So we can see pretty easily here how much improvement such a knowledge graph can give us in such a scenario. And this is all possible if we have what is called linked open data, right? So this means that we're actually publishing data on the web in a specific format that makes this kind of searches possible. And for this, the semantic web community has come up with a star rating system that would give you 1 star for even publishing data in a closed format like PDF. So, I mean, we can't do much with it, but at least it's there on the web, and potentially we could use it in some way. So you get 1 star. If you publish it in a structured format like XLS, you get 2 stars. If you publish it in a structured format that's open, like CSV, you get 3 stars because then there's already a lot that can be done with the data in terms of interpretation. If you do it as RDF, and RDF, as we will see a little bit later, is the standard format for knowledge graphs, you get 4 stars to actually publish the knowledge graph. And if you even link it to other knowledge graphs out there in a similar domain or that are more general, and basically contribute to be able to construct this kind of agents, then you get all 5 stars. So you've done a really good job then. Okay, so this gives us the possibility to do all those fancy things with knowledge graphs that we actually want to do. Yeah, so talking about knowledge graphs, again, what actually gives all the value and the information is the semantic part, right? And the semantic part is always associated with ontologies. Ontologies basically tell us what data in a graph means, because otherwise it would be just connected nodes and edges. And for a computer, it still wouldn't have too much meaning. Well, yeah, a user probably would interpret it anyways. So what are ontologies? I have a very simple example here. So let's imagine you're looking at restaurants and cuisines. So you model basically a kind of a restaurant ontology, and you can say, for example, we have different cuisines here, like American, Asian. Asian has subclasses of Chinese, Japanese, and Korean. Then we have also Mediterranean, and then there are also different types of restaurants, like Chinese, Japanese, and Korean restaurants. Right, and then for Chinese restaurant, we could define a constraint that tells us that it has to have some Chinese cuisine, right? Because from a Chinese restaurant, I would expect that it serves Chinese food as well, but it doesn't mean that it's disjunct to other cuisines as well, right? So they might also, serve sushi or some other food. So having this information, we could conclude on one side that if we have a query about a restaurant and want to consume Chinese cuisine, then the logical answer to that query would be a Chinese restaurant, right? But also what we could infer from the information that we have is that since Asian, the class Asian has subclasses of Chinese, Japanese, and Korean, and this type of cuisines are often served in Chinese restaurants as well. And those are non-disjoint siblings. So this means that they are very similar, and it's very likely that you might get this type of food in each of those 3 types of restaurants as well. Right, so it gives us actually the meaning to our graph and helps us find similarity and additional information and to reason about the information in the graph, what we have, so find actually new connections. So stepping back a bit and looking at the bigger picture, what the main goals of semantic web actually are is for one to build this type of models, right? To actually describe a part of the world, or in the end, the whole world in an ideal case, to understand this complexity and information that we have on the web, and then to compute the knowledge, so to reason about it, find new conclusions, find new connections in your graphs, and just advance your information to a further level, which is a very important part as well. And then the last step, basically, and this is also very important, is to exchange this information. So it has to be available to others. We need to share the knowledge that we have, because only then are we able to connect graphs and to do more advanced type of queries and reasoning and so on. So this is basically the linked open data step that we need in the end to have basically the next version of the web available to us. So if we put this into perspective with AI, as I said, it's a little bit of a competition traditionally between AI systems and semantic web, ever since semantic web as a research field came into being. And I've been to conferences a lot, especially International Semantic Web Conference, and I followed the developments in the last 10 to 15 years. And what I've noticed was that we're getting ever closer to using ML in semantic web and vice versa. So you can see if you look into papers published there or into workshops and tracks in the conferences, you can see that there is more and more interdisciplinary research between semantic web and machine learning, which tells us that there is some common advantage that we might achieve if we try to combine it. But traditionally, the goal of AI was to build intelligent machines that kind of mimic human behavior and that are able to make sense of very unstructured data. But the problem that AI always had and machine learning had and has still a bit is that you need a lot of computing capacity and very advanced GPUs, for example, if we're talking about neural networks at the moment, that to process all this information that's there. But so it's a little bit slow. And this is again the advantage of the semantic web that is able to reason over stuff pretty quickly and deal with large-scale information, but basically from another perspective, because you have to have information structured in a specific way first, right? So if we have a look into how this is basically done, we need to talk about languages a bit as well, because those are obviously essential to tell us how to structure this information to be actually able to produce knowledge graphs. So the most basic one is called Resource Description Framework, or RDF for short, which means that this is the standard format from the very beginning to represent knowledge in a distributed world, right? So we're thinking about connections in a knowledge graph on a very, very elementary level that are then distributed and shared and enlarged by connecting them to more and more information. So talking about knowledge, we have RDF that's designed for knowledge and not for data. So it's concerned basically with the meaning of information rather than what information actually represents or what can be concluded from it in the first place. And the thing is that in RDF, every single node or every single resource is actually something in the real world as well, right? So we could have people there, we could have locations, things, and so on. So everything is something in the real world as well, because our actual goal is to model a real world scenario. And by putting those entities together in a very natural subject, predicate, and object way, very much like in the English language, we can arrive at specific facts, right? So for example, if we use a triple, so this triple is called when you have a subject, predicate, and an object, you could use John, the state of being friends, and Bob, and then you might derive that John and Bob are friends having this connection in common, right? So this might be a very, very simple statement that you can form with RDF. And then on top of RDF, basically, we also have schema languages like RDFS and OWL. So very, very similar. You probably know about XML and XML schema. So XML is pretty meaningless on its own. But if you add a schema to that, then a machine can interpret it. You can actually work with the data. And this is exactly how RDF and RDFS and OWL work, right? So let's see an example. We have here Andrew, who knows Matt. So this is our first triple. Then we have Andrew, who has a surname Perez Lopez. Then we know that Matt knows John and that Ryan works with John, right? So very, very simple statements. And if we look into how this would be represented as a graph, we can see the following picture here. So we see Ryan, who works with John. Matt knows John. Andrew knows Matt. And Andrew's surname is Perez Lopez. But it looks pretty neat as a graph, and it gives us a very good impression of how those four people are connected. So if we inspect this in terms of RDF, For example, in the triple on the top, we have subject Ryan, predicate is works with, and object is John. And yeah, one other thing is, for example, if you look at Perez Lopez as such, so this is kind of a standard data type in semantic web called literal normally, which means that it's just a value and can never be a subject in a sentence, always only an object, because there is no no sentence we can build with starting with the standard data type. And then Andrew, for example, is a resource, so it can be both subject or object. And this is then how our graph will be connected further, and we can add more and more people who know each other to model the bigger picture. Yeah, in the real world, it would look more like this, because one thing to know as well is that we're always using unified resource identifiers, which means that every resource that we publish and model has to be unique on the web, right? Because just imagine the bigger picture. If you want to have linked open data and connect everything on the whole web, everything you model as well has to be unique, which is normally pretty easy because every person can have a website, so you can use the URL of your website as a URI and define your triples in a way that uses this unique namespace that you're modeling there. But in practice, this is always shortened down to some kind of namespace so that you don't have to type it out every time, luckily. Yeah, and then having this, what's really interesting is when we talk about inferencing, so we're trying to derive new information from the relationship that we have so that our graphs become more connected and more consistently integrated, right? More connected means you have a graph that has more and more connections because you were able to derive some new knowledge. But so looking at our simple graph just before, we could find new connections between who knows or who doesn't know each other just by adding, for example, the property of not knowing each other. We could already have a lot more information than we had in the beginning. Or we could just want to express a relationship like between apple and fruit. So every time you refer to an apple, you know that also refers to a fruit. Or you could have a restaurant in a specific location and then infer from there that this also means that this location also contains this restaurant, right? So either way you're browsing or trying to query the graph, you will come to this conclusion. So from the perspective of an inference engine or a reasoner, you would see that while the picture on the left side is how humans see the graph, the right side picture is how machines would see it, right? Because we have just any kind of random properties and resources. But for the machine, it doesn't really mean anything unless you have a schema, right? So while RDF provides a way to model information, it does not provide any specific meaning of this information as well. So the graph alone can only be interpreted as such as a graph by the machine, and you would still need a human being to tell you what all those resources actually mean. So therefore, what we actually need is a schema, as I already said, which is your vocabulary knowledge that is specific to a schema knowledge. So if we use RDF vocabulary, we need to have a well-formed RDF document. It needs to be read and processed by all tools that support RDF, which means RDF is a community-wide standard to do that. And those parts that are specifically defined by RDFS could not be understood otherwise by a parser if you didn't attach this schema to your RDF graph. Right, and here again you see the namespace that's normally abbreviated by RDFS. So let's have a look at an example, right? What can be done now that we have RDFS as well? We could define classes, much like a hierarchy definition of classes and subclasses. So for example, here we have the class bestsellers, which is a subclass of books. New York Times bestsellers, again, is a subclass of bestsellers. And paperback fiction is a subclass of New York Times bestsellers. And then you could have a specific book that is Water for Elephants, for example, that's of type paperback fiction, right? So the upper part was RDFS, right, where we assign classes and subclasses to each other. And the lower part is actually RDF, where you construct a graph and then have this type property telling you what this actually means, right? So this makes it possible for us to know that Water for Elephants is a book as well, right? And that paperback fiction is only a type of book, or only a subclass of book. Yeah, and then again, I'm not going to use too much time on OWL, the web ontology language. I just want to tell you that this is kind of a next step of RDFS, because it brings us more functionality. Because RDF is limited as an expression, so it would be very limited to this class type of system. Additionally, we could say, you know, what relationships or what is possible as a resource that connects relationships. So, for example, friends has to have a human domain and a human range. So both sides of friends have to be humans, for example, but not much more than that. So for that, we need OWL as the web ontology language that requires expressive representation languages based on logic, right? So OWL is based on first order logic. And even more than that, OWL comes with different flavors of description logic that allows us to use logical reasoning on the knowledge that we're representing in the graph. And OWL provides exactly this type of knowledge. Okay, so just these few informations about OWL that you need to understand why it is needed. And also, if you're wondering about the name, why web ontology language is abbreviated by OWL, this is a bit of a funny story because it refers to Winnie the Pooh books, where the owl in the story always spelled its name with W-O-L. And so the abbreviation for the web ontology language is OWL refers back to that. It's a little bit of a pun to the story. Yeah, so now that we know what how knowledge graphs actually look like, we might think the step further that I already mentioned before, and trying to connect machine learning and knowledge graphs, right? I mean, knowledge graphs are a really good thing, but they only evolve their full potential when you have some kind of advanced methods to complete those graphs and to actually not only use a standard reasoner, but also have something that gives you maybe probabilities of new connections and assumptions that you can make without complete information maybe. And this is where machine learning actually comes into play, right? So the questions that we need to ask ourselves in regards to machine learning and knowledge graph are twofold basically. So one thing is we could ask ourselves, what can knowledge graphs do to improve machine learning? And there's a lot actually that can be done, because machine learning has, as we all know, some limitations too, especially if the quality of data is not that sufficient, or maybe not that reliable. So we could use a knowledge graph, for example, to provide new dimensions to data. So we could add a new layer of information, new features basically, by building those connections that knowledge graphs provide us. We could also do pre-classification and better definitions of classes by using an ontology to add some semantics to it. We could use description logic as a restriction system, for example, and pre-processing layer to tell us, to limit data a bit and to shape it in a better form so that machine learning can do more with it. Or we could just label it in a more sophisticated way. But also what's very interesting in knowledge graphs when we think about use of them in machine learning is that they are able to validate the quality, basically, and appropriateness of the data set for a specific model, right? So just imagine nowadays you would have a data set, and then you would start, as a data scientist, you would just start trying out different models, compare the results, and then you would write a paper explaining why support vector machines perform better than a random forest for a specific problem. But imagine if you had semantic web technologies to do that for you, and you would be able to use restrictions on a knowledge graph, for example, that defines what quality of a data set makes up. And then based on this, you would have a suggestion for a machine learning model specific to your data set and your problem that has the most potential to perform best. right? So you could save yourself a lot of time by trying out different models from different categories, and then testing all this out, doing training all over again, by having more sophisticated suggestions what you actually should start with. But also on the other side, we have the question what machine learning can do to improve knowledge graphs, and there's also a lot. So as we know, knowledge graphs are really hard sometimes to complete because of the open world assumption, right? If we assume that information that's non-existent, we just don't know about it. But if we would use machine learning, as I said, for suggesting probabilities of this incomplete information, and then be happy with that in a specific scenario, it could help a lot to improve the completeness of knowledge graphs that we have. Also, we could use it for ontology matching, which is another problem that we have now in semantic web, but also reasoning support to get better reasoning results, and so on for the things that we're trying out. So putting this into perspective a bit, we could actually even almost say that knowledge graphs are kind of a new era of computing, right? Because thinking back how it all started was the so-called procedural era, where we had just raw data. Then we had some hard-coded rules that we used to build a program, and these programs then answered some questions for us that we had on the data, tried to explain a specific scenario or a specific problem, and that was it basically, right? Then machine learning came into the game, and once we had some answers, what we actually wanted to do were predictions, right? So we wanted to see how it then goes on after what we already had according to our information. So we started building machine learning models. Those would come up with rules and weights for models that would then help us predict the future or see, the whole picture of the data based on the answers that we already knew about. And then in the next step, if we bring knowledge graphs as well to the ball court, we can see that structuring information that way from a raw data set and using machine learning to complete the graph or as an additional supporting layer to machine learning, we could get to actual knowledge, right? So we could actually see behind the curtains and find answers that we never were able before with simple machine learning or even more procedural programs. So we would have these answers, we would have explanations, and we would be able to derive actual knowledge from that. And this brings us to the final question here, which I formulated as how to save the world from ignorance. Because you might agree or not, but I think that a huge problem in the world these days is ignorance. Right? Just thinking about people coming up with alternative facts, people believing social media too much, or lying politicians or whatever. So there are a lot of conspiracy theories for every single problem that we face nowadays in the world. Be it not believing that COVID-19 is real, because it might just be a scam from the face mask industry, or not believing that climate change is a real issue, and so on. So so we could actually use knowledge graphs to prove that this type of information is correct, and to actually tell something about truthfulness of information that we are faced with at the moment. So what I've done is I've picked 4 examples to show you how knowledge graphs can help make the world a better place that deals with exactly this type of problems that we're facing now. So just think about political agents. They're dealing with misinformation, right? So if you're reading an article about a politician or a political issue, you might think twice sometimes, because it depends a lot on how this is researched, how reliable the medium actually is that's publishing it, and so on. So it's very, very hard for you to find the truth there. Or you could think about fact checking from knowledge networks. So just hearing politicians speaking on TV and not being able to say if they're telling the truth or not. Or, for example, we could fight COVID-19 with linked open data, or even expedite climate change action with knowledge graphs as well. So let's have a look at those examples for a bit. So the first one is a very interesting one from Brazil, which shows us a knowledge graph about political connections in a specific region. And interesting thing here is that what is used here is provenance information, right? So information about which source people are using to publish statements, and as well as functions that people are occupying at a specific time, which helps us a lot with verifying if this information is really correct. But so if you look at this picture here, on the left lower part of the graph, you can see Andrea Sadi, who is a reporter and who has published an article. So she's a reporter for Global News, obviously, and she's published an article that is here shown in turquoise. And this article is about the connection of Simone Morgado and Jader Barbalho, who are obviously married, but they claimed the end dates of their marriage was 1st of November 2016. Right, so this article deals about this issue because there might have been some problems, you know, with occupying specific positions of power by relatives or by people who are associated to each other. And if we look at the whole picture of this graph, right, so we can see here that Simone Morgado is a congresswoman in the House of Representatives, and she has an office aide, Soane Castro, who is superintendent since the 3rd May of 2016 of the Fishing and Agricultural Coordination Agency. Now, this is part of the Ministry of Fisheries and Agriculture, where the minister was from 2nd October to 2015 to 1st of 2016. Helder Barbalho, who is again the son of Jada Barbalho, who was at the time married to Simone Morgado, right? So, so we can use this knowledge graph here basically to parse all this kind of information and you know, find some suspicious political behavior, some suspicious occupation of positions of power, and identify, you know, corruption in a political system, for example. Right, and the good thing here is also that you can use sources that you trust, right? So you can define in your provenance information which type of sources you actually trust and how what information these sources represent and what information is not valid basically if you publish it against each other, right? So you could find basically misinformation in articles this way. So a very interesting scenario that could be used to do a lot of good in the world, I think. Another thing is fact checking that you can do by knowledge graphs in a faster way than you could with pure machine learning. And here again, a combination of both would probably be very, very beneficial. So so just imagine you're watching TV, you're seeing President Trump talking, and he claims that Barack Obama is a Muslim, right? So what can you do? You could, for example, use a knowledge graph similar to this scenario here, where we have a knowledge base that's pulled from Wikipedia, and those info boxes that provide basically how people are connected to other information in Wikipedia. And then you could try to, after hearing such a statement, you can just try to verify how probable it is that it is true, right? So you construct a subgraph of your knowledge graph that you pulled from Wikipedia. By the way, DBpedia is the best at the moment to do that. And then you could just follow the links until you come to a conclusion or a connection to the actual statement that's been made. Right, so now to connect Barack Obama to Islam in this case, you would have to go to Columbia University, where he studied, which is part of the Association of American Universities, which has 2 universities that are from Canada. And at this point in time, Stephen Harper was Prime Minister of Canada, who is from Calgary, and the mayor of Calgary is Naheed Nenshi, who is Muslim. Right, so as you can see on this subgraph, it's a pretty long shot basically to connect Barack to Islam, And also what's remarkable here is that you need to use very general assumptions like Canada. So this connection here that's called Canada is very generic, which means that probability is very low for this to be of actual relevancy. And so based on this answer from the knowledge graph, it is very unlikely that there is any type of connection here. So again, so this is a very useful approach if you want to verify truth by speeches and by politicians that are made, or any other statements basically in social media. Then I have an example here for COVID-19, where linked open data is used in Singapore to basically show you clusters of infected people. So we can use knowledge graphs basically to connect locations. So in this example, we have a few locations that connect people who are infected. So those people in red had positive COVID tests, people in green had negative ones. And then if you represent this as a knowledge graph, you can see where infected people are clustered. So you can identify basically sources of spread of a disease like COVID-19 to make sure that you're doing proper lockdown measures and react in a way that saves the most human lives possible in such a scenario. And my last example is about climate change action. As we know, there's a lot of climate change action going on, but one problem here is also that people, or a lot of people, don't believe that climate change is real, which also means they don't believe in science. But the thing is how to prove that information is correct and how to find articles if you're looking for confirmation of facts that you're talking about. Right. So in this case, we have a knowledge graph that connects all articles published in about climate change action. Right. So if you're looking at a keyword, like here in the center of the graph, the keyword climate resilient infrastructure, you could come up with a lot of articles and documents that handle this topic and that show you proofs and scientific information about to support what you're talking about, basically maybe in a debate or in a paper to show that climate change is real, or the specific climate change action can be supported by articles. And also, if you look at the notes in green, it can show you which organizations are contributing to this type of actions, so that you could even coordinate actions to fight climate change in the most efficient way, basically. Okay, so this is what can be done, or just some suggestions that can be done with knowledge graphs to make the world a better place. At U Dublin, we have a small research group that has started to look into this type of research and topics, and we'll do a lot of work in the future to support saving the world from ignorance and making it a better place. So if you have any further questions, or you want to help us, you want to collaborate or whatever, just feel free to contact me anytime, and we can talk about future work. All right, so thanks a lot for this talk. I think we have some time for questions.